Okay, so we'll start off by looking at the second part of section 3.1. Okay, what they're going to do in this section is they're basically going to give you a formula and ask you a question if you plug something in, and it'll be like a yes-no type of question, or a true-false. So this first formula is basically just showing you the idea that if you put inverse sine and regular sine right next to each other like that, they cancel each other out. Okay, don't put the lines through it in your notes. I'll erase that in a second. But they cancel each other out, and the answer that you get is whatever is sitting right there. Okay, so let me show you with an example. Let's take the inverse sine of the sine of 47. And I'm going to do this in degrees. Okay, so when I hit enter, what do you think I will get? Yeah,
47.
I'm going to get 47. I get back the same thing I started with, because inverse sine and regular sine, they just cancel each other out. But that doesn't always work. In order for it to work, you have to plug in a number that's between negative 90 and 90. Okay, and we saw that's negative 90 to 90 yesterday. Okay, if you're in radians, it's negative pi over 2 to pi over 2. Okay, so let me show you what happens if you plug something in that's not between negative 90 and 90. Let's try 107. So 107. And I get back an answer, and there's a pattern to the answer I got back. You could probably figure out why I got 73 back if you look for a pattern. But the point is I didn't get back what I started with. Okay. So any questions on that formula? Basically when it works and when it doesn't. Okay, so let's look at this one. So in your book, they call this formula 2b. They call the first one 2a. That's not really important. What's the difference between 2a and 2b? They're close, but they're not exactly the same. Something that's different about them. Yeah, Ethan?
The inverse sine is in the parentheses.
Yeah, so now the inverse sine is inside. That's the inside function. Regular sine is the outside function. Okay, and these two things will also cancel each other out. And the answer that you get is whatever you plug in, as long as you're between negative 1 and 1. Okay, so that formula only works between negative 1 and 1. And if you're wondering, well, where does that negative 1 to 1 come from? If you take a look at this graph, and I think we looked at it yesterday, each tick mark going up and down is 1 unit. So looking at that graph, can anybody tell me what it looks like the highest that graph ever goes is? 1, and the lowest? Negative 1. So the fact that this graph goes as high as 1 and as low as negative 1, that's where this negative 1 and 1 are coming from. Okay, that's one way to explain it. Okay, so let's try it. Let's try the sine of inverse sine of 0.78. So I picked something between 1 and negative 1. I hit enter. Perfect. I get back the same thing I typed in. Let's try something that's not. Let's try like 1.5. All right, so 1.5. Now I hit enter, and it doesn't even give me back a different number like the first one. It doesn't even give me anything back. You can't even do it. And the reason you can't do it is because if you're trying to answer that question, it's kind of like trying to answer this question. Where do those two graphs cross? I just put a line at 1.5. The answer is they don't. They don't cross. It's impossible. Visually, that's the reason why we just got an error when we tried to type in 1.5. Okay. Any questions on that formula? When it works, when it doesn't? Okay, let's try another example. This one says, is the inverse sine of the sine of pi over 8 equal to pi over 8? The answer is either yes or no. All right, so first thing we want to figure out is what the criteria is you're supposed to be between. So we want to see, is this formula 2a or 2b? So Brady, which one is this?
2a.
Yep, I agree. It's 2a. Inverse is on the outside. 2a has it on the outside. And Brady, what is pi over 8? Degrees or radians? It's radians. So for radians, we're supposed to be between negative pi over 2 and pi over 2. Is pi over 8 between those two numbers? What do you think about Sam?
No.
No? Let's think of it as like a number line. Okay, so here's negative pi over 2. Here's pi over positive pi over 2. 0, put right in the middle. So you agree pi over 8 is a positive number, right? Because it's positive 3.14 divided by 8. How does pi over 8 compare to pi over 2?
It's a smaller fraction.
It's smaller, right? But you said it's still positive, right?
Yeah.
So that means it's somewhere in here. It's smaller than pi over 2. So that means it's to the left of it. But he said it's still positive, so it's more than 0. So does it fall between negative pi over 2 and pi over 2?
Yeah.
Yes, it does. So the answer here is yes. That one works fine. Sometimes it's a little trickier when it's a fraction, but that's kind of how you could think about it. Okay, let's try this one. Okay, same setup as the last one. Inverse is still on the outside. So we're looking to be between negative pi over 2 and pi over 2. Okay. Colby, how does 3 pi over 2 compare to pi over 2?
2's at the bottom.
It's what?
2's at the bottom.
Okay, well, if you were going to compare like less than, greater than, or equal, how does 3 pi over 2 compare to pi over 2?
It's greater.
It's greater than, right? It's pi over 2 tripled. So you tripled pi over 2. So if you take pi over 2 and triple it, are you going to be between negative pi over 2 and pi over 2?
No.
No. You're much bigger than pi over 2, 3 times as big. So the answer here is no. That would not work. All right, let's try this one. Okay, so this said the sine of the inverse sine of 1.5, is that equal to 1.5? Okay, so Luke, this time are we dealing with formula 2a or 2b?
2b.
Yep, this time it's 2b because the inverse is on the inside. And what's the restriction we're supposed to be between?
Negative 1 and 1.
And did what I plug in here fall in between what you just said?
No.
No. So that doesn't work. Yep.
Can you go back up to those formulas real quick? Thank you.
Okay, and the last one, that one is also going to be formula 2b because the inverse is on the inside. And this time it's 0.6. It's going to be 0.6. So, Jermichael, formula 2b, does 0.6 fall in the restriction it's supposed to?
0.6?
Yeah.
I'll say yes.
Yes. What is the restriction again?
Negative pi over 2 and positive pi over 2.
When inverse is on the outside, it is, but for this one, it's on the inside.
Oh.
What's the restriction when it's on the inside?
Wait, are you talking about like negative 90? No? From yesterday?
Nope, just what's right up here.
Oh, is it negative 1? Between negative 1 and 1?
Yeah, it's between negative 1 and 1. So inverse is on the inside. We're looking to see, are we between negative 1 and 1? I look at the number I plugged in, 0.6, and the answer is, that's why it's yes. 0.6 is between -1 and 1.
Oh.
Okay. The only other way you could see a question like this worded to make it a non-yes/no question is something like this. Instead of saying is and then giving you something, they might say simplify the sine of the inverse sine of 0.6. For that kind of problem, don't write yes. Okay. Yes is not an answer to a simplified question. What would be the answer to that? 0.6. That's the only other way you could really word the type of question I'm asking you right now. Okay. So any questions on inverse sine? The inverse sine and sine formulas. Okay, so let's look at same idea, except now for cosine. Okay, your book calls these two formulas 4a and 4b. So, if you have inverse cosine on the outside, regular cosine on the inside, that formula will work as long as you plug in a number between 0 and pi. So this restriction has to do with what we learned yesterday, the 0 to 180. And then when you switch it, put the regular cosine on the outside, the restriction here has to do with how high and low the graph of cosine goes. And I think I showed a graph of that one yesterday too. Anybody remember how high and low the graph of cosine went?
0.
It went higher than 0. Remember?
180.
So 0 to 180, that's something else, Jermichael, you're thinking of, but that applies to this one. This one is a little different. This doesn't have to do with the 0 to 180. Okay. Let's look at the graph of cosine again. Okay, I'm just going to graph it with everything else I already have. What's the highest and lowest that it looks like cosine goes?
1 and -1.
1 and -1. So it's exactly the same as sine. Same restriction. So for the A formula, the restriction comes from the stuff we did yesterday. For the B formula, it's the highest and lowest that the graph would go. Okay, so we'll try just a couple examples of this one. Okay, so it says, is the cosine of the inverse cosine of 0.95 equal to 0.95? So it is a yes/no question. And Liz, is this one like 4A or 4B?
4B.
Yep, the structure of it. Regular is on the outside, inverse is in the inside. That's 4B. And Jill, what am I supposed to be between for x on formula 4B?
-1, +1.
Yep. And is the number that I've plugged in here between what you just said? Yes, it is. So the answer here? Yes. Okay. And we'll just try one of the other type. Inverse cosine of regular cosine. Okay. I just told you it's the other type. So this is formula 4A. Ben, what am I supposed to be between for formula 4A?
0 and 180.
Yep, we're supposed to be between 0 and 180. Did I plug in a number between what you just said? No, I plugged in 210. So it's not that you can't do it. You can type that in, but you're not going to get 210. Okay? That's the one, if you type it in, you'll get something different back. On the B formulas, that's the one that if you don't type in between -1 and 1, you won't even get an answer back. Okay, okay, so that's the idea for the inverse and regular cosines. Questions on those? Okay, and what do you think the last sets of formulas we're going to look at? What function do you think they deal with? The tangents. Yep. Okay, so let's see if we can remember this one from yesterday. The restriction. What did we have to be between when we did inverse tangent? Yep.
Negative 90 and 90.
Negative 90 and 90, except this time there's no equal to's. Okay, so any questions on that? Now, formula 6b, this restriction is a little trickier to figure out because I never showed you the graph of tangent. But I'll show you the graph, and remember that restriction is how high and low the graph goes. Okay, so let's take a look. I'll get rid of the other stuff so we're not looking at 4 things at the same time. So tangent is a very different looking graph than the other ones. Definitely has a pattern to it, but it's not a wave. How high and low does it look like that one goes? Any guess? Yeah, go ahead, Ethan.
Infinite.
Yeah, it does. You can zoom out, but it doesn't stop. It just goes up forever, and it goes down forever. So the restriction here is, there isn't one. X can be any number that you want, as high or as low as you want to go. Okay, so we'll just try one example of this one. Same idea as all the others. Tangent of the inverse tangent of 30.4. Would that equal 30.4? Okay, so Austin, is that one set up more like 6a or 6b?
6a.
All right, how come?
Actually, would it be 6b because it's not a degree?
I agree that it would be 6b, but not because it's in radians. Why is this 6b? It doesn't have to do with whether you plug something in that's in degrees and radians. Yep.
Is the inverse tangent is on the inside?
It has to do with where the inverse tangent is. Is it on the inside? Is it on the outside? It's on the inside. That's why it's 6b. Okay. So Nathan, is that going to work?
Oh yeah.
Yeah, how come? What's my restriction here?
There is not.
There is none. Exactly. I like the enthusiasm. Yeah, it's definitely going to work. Okay. Questions on that? Okay, so that's the last half of section 3.1. Okay, so last section we're going to look at this week is 4.1. Right now the plan is to split that into 2 days. And just as a reminder, if we don't have class on one day, we will do 4.1 the next time we have class, test on Friday. If we don't have class for 2 days, then we'll have 4.1 on Friday, and then we'll have a take-home test that would be due on Monday by the start of class time, 8:30. Okay. And that's Monday right after the weekend, not the next academic Monday. We'll see what happens. All right, so in this section, if you've done SOHCAHTOA, Pythagorean theorem, that's the kind of stuff we're going to look at here, but you might have not done that with inverse trig. So we'll eventually kind of combine what we learned yesterday with what we're doing now. Okay, but I don't think that comes till part 2 of this section. All right, so first of all, since we're doing right triangle trig, let's just make sure we know what a right triangle is. Anybody tell me what a right triangle is? Yep.
A triangle that has 60 degrees on all 3 angles.
So a triangle that has 60 degrees on all 3, that's equilateral.
So there's a 90-degree angle and then 2 others. One of them is 30. The other one is 20.
Not quite. Part of what you said is good.
So there's a 90-degree and then
There's a 90-degree angle. Yep, just stop there. There's a triangle with a 90-degree angle. What the other angles are, they can be anything, as long as you follow a certain rule about triangles and what the angles have to add up to, and we'll get to that in a minute. So 90-degree angle, the side across from the 90 is always the longest side, because that's always the biggest angle in a right triangle. Has to be. There can't be another angle in the triangle that's bigger than 90, and we'll talk about that in a minute. What's the name of the side that's across from the 90, and it's the longest side? Yeah? The hypotenuse. And does anyone remember what you call the two short sides?
The legs.
The legs. So there's just kind of a general diagram of a right triangle. Okay, these other two angles, here and here, they are going to be acute angles. And they have to be, because of what all the angles have to add up to, and we'll get to that. But for now, I just want to know, what is an acute angle? There's actually two parts to it.
Angle is less than 90.
It's less than 90, that's the first part, but it also has to be something else. Anybody know what else it has to be? Because I could definitely name a number that falls into what Alan just said that's not acute. Yep?
Greater than 0.
It's got to be greater than 0. And if you're like, well, are angles ever negative? Yeah, we've talked about negative angles. But in a triangle, we don't deal with that. So an acute angle, less than 90, more than 0. Okay, any questions on that? All right. Pythagorean theorem. So the Pythagorean theorem is a theorem, meaning it's something you can prove actually pretty easily. It's not that hard to prove with a picture. But what is the Pythagorean theorem? What does it have to do with in a triangle? So triangles have sides and they have angles. What does this theorem have to do with? Yep.
Sides.
It has to do with sides. Yep. And can anyone explain to me what the Pythagorean theorem is? How would you explain what that is to someone? Yeah.
A2 plus B2 plus C squared. Like,
All right. Now pretend you're talking to someone in like maybe like 6th grade. They probably wouldn't quite understand what you mean. They're like, huh? What's A2? What's a B2? And what's a C? Because we don't have A, B, and C on the board right now.
each of the legs, like square each of the legs equals the square of the hypotenuse.
Okay, yeah, we're pretty close. It's square each of the legs and then add them up. It equals the square of the hypotenuse. A lot of times people write it as a squared plus b squared equals c squared, but you just have to explain what a, b, and c are. You could use a, b, c, x, y, z. It doesn't really matter what letters you use. The idea is one leg squared plus the other leg squared equals the hypotenuse squared. Okay, so that's a theorem that we can use. I think we're going to mention it eventually, but I've kind of hinted at it a couple times. There's a restriction on all the angles in a triangle. What do all the angles have to add up to? At least on a flat triangle, which is the kind we're dealing with.
180.
Yep, they have to add up to 180. And if you're thinking, well, what other kind of triangle is there besides a flat one? There's curved ones. If you think of like connecting the North Pole, Boston, and London, definitely makes a triangle. But the surface of that triangle is curved on a sphere. So it's very different than the kind of triangle we're dealing with because it's not flat, because the Earth isn't flat. It's bent on a sphere kind of thing. But our triangles we're dealing with are going to be flat. All right, so before we can really talk about the trig functions, which I'm going to tell you the definitions of in a second, all 6 of them, I need to define 2 terms, opposite and adjacent. Okay, these 2 terms are what we call relative terms because they don't always indicate the same thing. It depends on your perspective. Okay, they're kind of like the terms left and right. If you tell someone to go left, left doesn't always mean the same thing. It depends which way you're facing. For me, left is the door. For you, that's right. So depending on your perspective, things change. So opposite is always the side that's farthest away from the angle you're referencing. In this problem, I'm specifically referencing the angle in the lower right. Okay? That's the Greek letter theta. So this is opposite. This is adjacent. Opposite is the side that's farthest away. It's the side that if you got rid of it, it wouldn't have any effect on this angle at all. I could erase the opposite side, and I would still have an angle where I just circled it. If I draw the same triangle again, and now I'm referencing the angle at the top. Now the top is my perspective. Pretend like you're standing where the angle is, and you're looking out. Opposite is the side that's farthest away. Adjacent is the side that's right next to the angle. Okay, another way to define adjacent, and I'll scroll down to it right now, is adjacent is one of the sides that if you erase the adjacent, you wouldn't have an angle anymore. So it forms one of the sides of the angle being referenced. And it's not the hypotenuse. So if I erase the adjacent and get rid of that, I don't have an angle there anymore. It's open. There's no other side to the angle. So adjacent is the side of the triangle that's right next to your angle. It forms one of the sides. And it's not the hypotenuse. Okay, the hypotenuse is more of, it's not a relative term, like opposite and adjacent. I call it more of like an absolute term. It's kind of like the word or the direction up. It doesn't matter which way we face in this room, whether you're facing the front or I'm facing the back, up is the same direction for everybody. Okay? Left and right changes, but up doesn't. Okay? Hypotenuse doesn't either. Regardless of what perspective you're viewing in the triangle, hypotenuse is always across from the 90. That doesn't change. Okay, and I already mentioned that idea, opposite and adjacent being relative to your perspective. Okay, any questions on the terms opposite and adjacent? Okay, now that we have an idea of what those mean, I can define for you the 6 trig functions using those terms. So we did this before as like sine was y, cosine was x, tangent was y over x. This is pretty much the same thing, just using different words. So sine is the opposite side divided by the hypotenuse. Cosine is the adjacent side divided by the hypotenuse. And tangent is the opposite divided by the adjacent. And when I write opposite and adjacent and hypotenuse, you could put the words length of in front of all of them. Length of adjacent divided by length of hypotenuse. So, trig functions are all ratios. A ratio is when you compare two things using division. That's what these are. It's a ratio of two side lengths in a triangle. And when you divide, let's say like your adjacent side was 5 centimeters, your hypotenuse was 8 centimeters. Centimeters cancels. Okay, we talked about that kind of the first week. Same units in the top and in the bottom, they cancel out. So trig functions don't have labels. They don't have any units to them. They're just a pure number, 5/8. Not 5/8 centimeters, not 5/8 inches. The unit cancels out. It's just a number without any other label. Okay. And now to get the other three. What did we do with the 3 on the left last week to get the 3 on the right? Okay. Flip them. So now all we're going to do is flip them. So cosecant is the length of the hypotenuse over length of opposite. Secant is hypotenuse over adjacent. And cotangent is adjacent over opposite. Okay. Any questions on those 6 definitions? Okay, so we're going to do kind of the same thing we've done before. They're going to give you a picture, maybe they'll give you a sentence. They're going to ask you for all 6 trig functions. Per problem, I will only ask you for 1. Okay, but we'll practice all 6. Okay, so this one, they give us a picture, and they ask us to find all 6 trig functions. Now, with what I have right now, I'm not ready to do that. What am I missing that I'm going to need in order to complete all 6 of those equations? Yep. I have to find the hypotenuse. And as long as you have 2 out of 3 sides in a right triangle, you can always find the side you're missing using what? How do you get the side you're missing? Yeah? You use the Pythagorean theorem. So you can call that C or X, whatever you want to call it. Set up the Pythagorean theorem. Leg squared plus leg squared equals hypotenuse squared. Now we just do it out. Casey, what's 3 squared?
9.
And then 4 squared?
16.
And if you add the 2 things you just said together?
25.
So we get 25 equals C squared. And Sean, I don't want C squared, I just want C. So what do I have to do on both sides?
Squared.
It's already squared.
Square root.
Square root, yes. So square root. And Kyle, square root of 25
5.
is 5. So in this problem, I happen to get a nice answer for the hypotenuse. And there's a name for that. Does anybody know what that's called when all 3 numbers in a right triangle come out without any decimals? It's called a Pythagorean triple. A Pythagorean triple. 3, 4, 5 is one of them. 5, 12, 13 is another one. There's an infinite amount of them, okay, where the sides all come out nice. Now, if you said something like, well, 30, 40, 50, yeah, that's another Pythagorean triple, but it's just this one 10 times as big. Okay, when I say there's an infinite amount of them, I mean an infinite amount of different ones, not just multiples of 3, 4, 5. Okay, like 5, 12, 13 is totally a different shaped triangle than 3, 4, 5. And if you're in carpentry or maybe some other trades, a lot of times they use that idea to check a doorway to be square. So if you had a doorway and you measure down 3 feet, over 4 feet, you can measure across, and it should come out to 5. If it doesn't, that means your doorway is not square. So same thing with a foundation, except you could make a bigger version of it. Measure 30 feet on the foundation, 40 feet, and then the diagonal should be 50. And if that's true, then you made a square foundation. Okay, so let's go through and find our trig functions. How about Brady? Can you tell me what the sign would be?
4 or 5.
Yep. 4 over 5. And we just leave it like that. We never write it as a decimal, like 0.8, and don't do anything like that. Just 4/5. Okay. Abby, how about cosine?
3.
Yep, 3/5. Caitlin, tangent?
4/3.
4/3. And now, once we have the 3 on the left, we don't really have to think too much about the 3 on the right. Cassandra, what do I have to do with these 3 to get the other 3?
Flip them.
Just flip them. So 5/4, 5/3, and 3/4. Okay. So that's how you find all 6 trig functions. Now, we didn't find how big this angle is. Okay. I still don't know how big it is. We're going to look at that tomorrow. But any one of these 6 facts, if you just told me one of them, I could tell you how big the angle is. Okay? And it would have to do with getting rid of sine. So you might, if you remember from yesterday, there's a function we can use to cancel out sine, inverse sine. And if you did that on each side, inverse sine would cancel regular sine. Just find the inverse sine of 4/5. That's the size of the angle. But again, we'll look at that more tomorrow. Since the hypotenuse came out nice here, we didn't have to worry about square roots. But all the same rules with square roots still apply. If that came out to a square root, then sine and cosine would have had square roots in the bottom. Okay? You can't leave square roots in the bottom. So any questions if you have something like that? How to get the square root in the top? Can someone just remind me, how do you get it in the top if you have to do it? Yep.
You multiply the top and the bottom by square root.
Yep. Multiply top and bottom by square root 3. And that's what I'd be looking for your answer. Okay. No decimals on this stuff. Tomorrow, yes, we'll use decimals, but not for that. All right. Complementary angles. Anybody remember what it means if 2 angles are complementary? And that's a hint. You have to have 2. You can't just draw a picture of one angle and say it's complementary. You have to have 2.
Yep. 2 angles that will add to 180.
That's supplementary. 2 angles that add to 180. It's 2 angles that add to 90. A lot of people mix those up because usually you study both of them together. But complementary angles are angles that add up to 90. And the next sentence ties in with something I said earlier. Okay, I'm claiming that the 2 acute angles, the 2 angles that are not the 90, are always complementary in a right triangle. Why? Why do the 2 angles, this one and this one, the 2 ones I just checked off, why do they always have to be complementary? Yep, Joe?
Because the right angle is 90 and the triangle can only be 80.
Yep, the right angle is 90, so those 2 have to be 90 together. So the 2 acute angles are always complementary. Always. Okay, keep that in mind. Okay, so now I'm going to show you something else. I'm going to show you what's called cofunctions. Okay, and once I explain what these are, then we're going to tie the idea of cofunctions and complementary angles together in a theorem. Very concise, very simple theorem. Okay, so there's 3 pairs of cofunctions. Okay, if we go back and look at the 6 trig functions, cofunctions are when you take a function and then just put the word co in front of it. So if I said to you sine, what do you think the cofunction would be?
Cosine.
Cosine. Sine, cosine. What if I said secant? What do you think the cofunction of secant would be?
Cosecant.
Secant, cosecant. Okay, that's another pair of cofunctions. And what about if I said tangent? Put the word co in front of it, cotangent. So what I've just put boxes around, I'm going to write them down, but those are the three pairs of cofunctions. Sine, cosine, secant, cosecant, tangent, cotangent. Okay, so let's look at this diagram and let's look at a few things. Okay, so I've labeled the two sides here alpha, A and B. And in trig, usually we use Greek letters to represent the angles, English letters, lowercase letters for the sides. That's how your book does it. Okay, some books use capital letters for angles, lowercase letters for sides. All English letters. I think it's confusing to use all English letters because if instead I made it a capital A and I made the side a lowercase a, and you said to me, how did you find A? I wouldn't know what you're talking about. You'd have to say, how did you find lowercase a or how did you find capital A? So then we have to distinguish. The other thing is on paper, some letters can look the same. Like what if you use the letter C? Capital C, lowercase c, without any context of other letters around it, they look the same. So if we use Greek letters for angles, we always know Greek letters are angles. English letters are always sides. Less confusion. Okay. And if I scroll up, we said something earlier. What's the relationship between alpha and beta? What kind of angles are they in this right triangle? Yeah? They're complementary. Okay, keep that in mind. Alpha and beta are complementary. So let's find a couple things. Let's start with the sine of alpha. I'm going to do this a couple times and see if you notice a pattern. Okay, so from the perspective of alpha, you're standing right there at alpha. We need opposite over hypotenuse. Right, so Nathan, what would be the sine of alpha?
A over C.
A over C. Any questions on that? Now I'm going to find something else, but I'm going to find something very specific. I'm going to find the cofunction of sine. That's cosine. So I'm using a cofunction now from what I started with, and I'm going to use the complement of alpha. What is the complement? Beta. Alpha and beta are complementary. So I did two things. From the first problem, I found the cofunction, and I used the other angle, the complement. Okay, so cosine beta. Sam, what's the cosine of beta come out to?
Isn't it adjacent over hypotenuse?
Yep, it's adjacent over hypotenuse.
So it'd be A over C.
Yes. A over C. If you compare the sine of alpha and the cosine of beta, the answers are the same. So, cofunctions, complementary angles. Okay, let's try that again. Let's just pick something different. Let's do tangent of alpha. Now, before I even calculate it, can anybody tell me what's the other thing that I'm going to find? What's the cofunction of tangent? And then what's the complement of alpha? Oh, Brady? Not sure? Let's start with the cofunction for tangent. Cotangent. Yep. So we got cotangent. We're going to find that. And what's the complement of alpha? Beta. Alpha and beta are complementary. Okay, let's find each of those and see what happens. So Ben, let's start with tangent of alpha. Tangent is opposite over adjacent. So what do we get for that?
A over B.
Yep, A over B. Now cotangent is adjacent over opposite from the perspective of beta. Adjacent is A, opposite is B from that perspective. So we got the same thing again. And that's going to keep happening. If you use cofunctions of complementary angles, you always get the same answer. And that's the complementary angle theorem. Cofunctions of complementary angles are equal. So let's look at a few examples on the left and see if you can tell me what I would have on the right hidden underneath the gray box. Okay, to figure out what's on the right, step 1, think of the cofunction. Step 2, think of the angle that would be complementary with the one I gave you. Okay? Complementary means it adds to 90. So anyone think they can tell me what the first one would be? Casey?
Cosine of 60.
Yep. Sine, the cofunction is cosine. 30, the complement is 60. And if you're unsure or kind of doubtful, you could check it. The sine of 30, 1/2. Cosine 60, 1/2. They come out the same. The point is not to know that they're both 1/2. We don't care about that. All we care about is that they're the same. Okay, how about tangent of 15? Okay,
Cotangent of 75.
it would be the same as cotangent 75. I'm not going to type it in and show you, but it would be. And the last one, how about secant 40? What would secant 40 be the same as? Jill?
Cotangent of 50.
I like the angle. It's definitely going to be
I mean cosecant.
50, but yeah, it's going to be cosecant. Okay, so where would you use that? Okay, I'm going to show you a kind of problem where that idea would come up. Okay, I want to calculate this out. Okay, and this might be the kind of problem where I just ask you to explain your reasoning. Why did you get what you got? Okay, let's look at the functions. Abby, sine, cosine. What are those called again? Not sure. How about 15 and 75? What are those called?
They're complementary angle.
They're complementary. How about sine and cosine? Yep,
Cofunction.
those are cofunctions. And what did we just say about cofunctions of complementary angles?
Yeah, 90.
No, not if they add up to 90. It was the complementary angle theorem. It says cofunctions of complementary angles are equal. So that means we're dividing two things here. If you ignore the minus sign in front, we're dividing two things that are equal. So when I do that out, what would I get? Yeah,
-1.
we get -1. The sine of 15 is exactly the same as the cosine of 75. So you're dividing two things that are the same, you get 1. There's a negative in front, so you throw a negative in front of your answer. That's the kind of question you would see involving that theorem. Okay? Okay, let's try this one. The tangent of 12 minus the cotangent of 78. Okay, how about Jamichael? Tangent, cotangent. What are those called?
Not sure.
You want to help him out? What did we just say those two things are called? You put the word co in front of it. Tangent, cotangent are cofunctions. All right, I'm going to give you one more shot. Right? 12 and 78. What are 12 and 78 called? Together, they form a pair of blank angles.
It's not complementary, right? It's not acute angles?
Together, each one individually is acute, but what do they add up to?
290.
They add up to 90. And what did you just say? Angles that add up to 90 are?
Complementary.
Yeah, they are complementary. So yeah, we have cofunctions of complementary angles. How about Austin? Cofunctions of complementary angles are always cofunctions of complementary angles. Cofunctions of complementary angles are equal. So we're subtracting two things that are equal. What do you get when you subtract two things that are equal? Caitlin? Zero. Alright. So when you subtract two things that are equal, you get 0. So what is the tangent of 12? I have no idea. I have no idea. What is the cotangent of 78? No idea. But I know that the tangent of 12 is the same as the cotangent of 78, whatever it is. So if I subtract two things that are equal, I get 0. Alright. Does that idea make sense?
It just turns to 0.
It just turns to 0 because you're subtracting two things that are the same. Just want to make sure I'm not losing people on that. I'm a little concerned. But we're okay with that? Okay. So that idea works with division and subtraction. What about addition? If you add two numbers that are the same, do you always get the same answer? Like if you subtract two numbers that are the same, you always get 0. I don't care what the numbers are. But when you add, does that work? No. If you add two numbers that are the same, you get the number doubled. So this trick doesn't work with addition. How about multiplication? If you multiply two numbers that are the same, do you always get the same answer? Okay.
Can you repeat the question?
If you multiply two numbers that are the same, do you always get the same answer? Like 3 divided by 3 is 1, 12 divided by 12 is 1, a million divided by a million is 1. They always come out the same. But does that work with multiplication?
No.
No. If you do 2 times 2, that's a different answer than 6 times 6. So when you multiply two numbers that are the same, you get the thing squared. Okay, so the trick doesn't work there either. Okay. So you'll see something, probably 1 or 2 questions on the test kind of like that. And I might ask you to just explain why did you put -1 or why did you put 0. Because you could just type it in on the calculator and get it. Okay. But I just want you to understand the complementary angle theorem. Great. So any questions on that? All right, so that's the first part of 4.1. So the homework, page 187, that's the yes and no kind of questions. So 46 to 51, 53 to 55, all. So they're all either true, false, or yes, no. And then page 255, 9 through 21 odd, that's practicing the sine, the cosine, the tangent, all that stuff. And the last 2 problems we just did. Okay, so just a couple reminders. So if we don't have class on one day, so one day of no class, then the test is Friday. 2 days of no class, test will be take home. Get the test Friday. It would be due Monday. What's the date on Monday? 3/12. At 8:30 a.m. Eastern time. Oh, you'd be surprised.
Eastern Standard Time.
Yeah, right, Eastern Standard Time. So 8:30 a.m. late tests equal 0. Okay, if you are on co-op or you're out, you can, so these are your options. Bring in person. Do not leave it under my door. If you just say, oh, I put it under your door and it disappears, sorry. So bring in person. Give to me. Email. Make sure you don't email the other Mr. Hager, because if he gets it, he'll just click delete. So that's no good. Email, make sure you know who I am. Email, I think that's really your only other option. Either bring it to me in person or email. Okay.